Okay, so in case anyone doesn't know, I'm Bob Frater-King. I run the PhD and MLT programs in the LTI. I've been there since before the LTI existed. And we've been having people this semester in memory of Jaime Carbonell, who passed away last February. We've been having his oldest students introduce his newest students. And so Jaime got his PhD at Yale in 1979. And I started my PhD at CMU with him in 1979. He went through undergrad in 3 years and did his PhD very quickly. And I was really, really happy that I did not know at the time that he was only 2 years older than me. I knew he was young, and I had worked for a year or two in between undergrad and grad school. So I was slightly old and he was very young for a professor. And I was one of the 2 students who started with him in the fall of '79. He actually had 2 graduates before me because they gave him a graduate student when he showed up. And then the big tragedy of my grad school career was that Tamita started after me and finished before me with the same advisor. So I was crying quietly in the back of the room when he did his defense. And when I finished in '86, I was so busy desperately trying to finish that I did not notice Jaime starting the Center for Machine Translation, which turned into the LTI. I was really surprised later to find out, well, I do remember a demo or something, you know, but I was just trying hard to get out. And so anyhow, it's my great pleasure to introduce 2 of his very recent students, Shruti Rijhwani, and then afterwards Zirui, Edward Wang will talk. They'll both be talking on different kinds of cross-lingual transfer. Shruti is going to talk on zero-shot neural transfer for cross-lingual and entity linking.
Hi, everyone. I'm Shruti, and I'm a PhD student at the LTI. And today I'll be talking about our work on zero-shot neural transfer for cross-lingual entity linking. And this was a collaboration with JT and my advisors at the time, Graham and Jaime. So I'm going to start with introducing the task of entity linking. And then I will dive into the specific challenges of doing cross-lingual entity linking, particularly in the low resource setting where you don't have a lot of data to train your entity linking model. And then I'll talk about our proposed model as well as how we improved low resource cross-lingual entity linking without relying on too much training data. So just as a brief introduction, we all know that natural language contains entities like person names, organization names, and location names, and so on. So entity linking is essentially the task of associating these named entities, which can be extracted from natural language text, with their corresponding entries in a large knowledge base like Wikipedia or DBpedia or other large encyclopedias like that. So for example, we can see these 2 sentences contain the entity Carnegie Mellon University in 2 different forms. And the goal of entity linking would be to identify the appropriate Wikipedia entry for all forms of the same entity. So ideally, we should link both the forms of CMU to the Wikipedia article for Carnegie Mellon University. So knowledge bases contain a large amount of information about each entity. And this information is typically in a structured form. So for example, if you look at the Wikipedia page of a country, you would see in the info box information about the capital and the population of that country. And having such structured information is useful for downstream applications like document understanding, event coreference, and other information retrieval tasks. So in this work, we focused on the cross-lingual setting of entity linking, where you link entities in one language to a knowledge base which is in another language, such as linking the entity Carnegie Mellon University in multiple different languages to the same English Wikipedia entry. And this is often useful because because a lot of the structured information we have is particularly on things like Wikipedia and other large databases like this is primarily in English, but we also want to know this information about entities which may be written in another language. And this is kind of where the cross-lingual setting comes into play. So entity linking typically has two steps. So the first step is candidate retrieval, where a short list of candidates from the large knowledge base are collected based on the input named entity that we're trying to link. And the second step is a disambiguation step, where the system decides between the short list of candidates and identifies the best knowledge base entry, which that is the appropriate link for the input named entity. So the methods used for disambiguation are typically more sophisticated and computationally expensive, which makes it impossible to run them on the entire knowledge base of millions of entries. So this is kind of why we need candidate retrieval, because these algorithms are typically faster and are necessary to reduce the search space for the disambiguation algorithm. And while they aren't as precise, they are optimized for speed and recall. So in this work, we focus on the candidate retrieval step in the cross-lingual case, where we try to generate candidates for an input named entity from some source language and try to link it to an English knowledge base. More specifically, we look at how we can generate candidates for lower resource language, where existing methods don't work very well because they rely on resources that are typically very limited or unavailable for these languages. So most existing methods for cross-lingual candidate retrieval attempt to translate the named entity, the input named entity from the source language to the target language of the knowledge base. And once this is done, once the entity is translated, simple string matching methods can be used to find appropriate candidates in the knowledge base. And most previous work relies on links between Wikipedia pages, which basically connects the article about the same entity between the Wikipedias of different languages to construct a bilingual dictionary. And this dictionary is then used to translate the named entities that need to be linked to the knowledge base. So around 300 languages have their own Wikipedia. And for some languages, the Wikipedia is really large. There are many articles, and high coverage bilingual lexicons can be extracted from these Wikipedia since they have over 1 million links to English, which is usually the target knowledge base. However, for lower resource languages like Tigrinya and Lao, far fewer articles and language links are present. And this makes it difficult to apply existing methods for candidate retrieval that rely on these links to translate the input named entity. And if we have to scale up to a large percentage of the world's languages, Wikipedia and other bilingual resources usually don't exist in most of these, and performing cross-lingual entity linking with existing methods is more or less infeasible. So as an alternative, we propose a method for retrieving candidates that doesn't rely on any bilingual resources in the source language itself for training the model. Instead, we leverage data from high resource languages, which is far more easily available, and use that to train the entity linking model. We then transfer these trained models to the low resource languages in a zero-shot manner. So we don't do any additional fine-tuning or joint training, and this removes the need to have any data in the low resource language at all for training the model. So first, let me introduce the entity linking model, and then we'll talk about the specific experiments that we do in the languages that we apply it on. So as in most existing work, English Wikipedia is used as the target knowledge base, so that's what we will use as well. So the primary goal here is to identify the English Wikipedia article that is the most appropriate link for the input entity. So the article that we select as the most appropriate link is based on some scoring function that computes the similarity between the input entity and the Wikipedia article in question. So since we don't have any training data in the source low resource language, we instead train the model to perform cross-lingual entity linking between some high resource language and English. So we use 2 character level LSTMs. So the first encodes entities from the high resource language, and the other does the same for all the knowledge base entries, which are in English. And the encodings from each LSTM are vector representations of the input strings in the high resource language and in English respectively. In order to compute the score for the specific English knowledge base entry, we use cosine similarity as the metric, and this gives a score to each entry in the English knowledge base. In order to train the model, we use parallel entities between the high resource language and English. And these are easily available from bilingual lexicons and Wikipedia language links for high resource languages. And they're quite, and typically we can get quite a few of them and enough to train the model. So for example, parallel entities like United States, like in English, and in a high resource language like Indonesian. So we're basically trying to get the model to learn entity linking between the high resource language and in English. So since we're effectively trying to rank the knowledge base entries for linking, we use a max margin loss with negative sampling as our training loss function. This forces the cosine similarity with the correct knowledge base entry to be at least a certain margin apart from the score with an incorrect knowledge base entry. And during implementation, we choose the incorrect knowledge base entries based on the current mini batch. So when applying the trained model to an unseen entity, the model should ideally assign the highest cosine similarity to the knowledge base entry that is the most appropriate link for the input. But we actually don't want to use our model with to do entity linking for a high resource language. Models already exist for that. So the first thing we do in order to use our model with a low resource language is zero-shot transfer. So consider an input entity in Javanese, which is a relatively lower resource language. And this is same entity as we saw on the previous slide, but in Javanese, the United States. So we simply encode the input entity using the LSTM trained on the high resource language. So for Javanese, we might use an LSTM that is trained on Indonesian. If the high and low resource languages are closely related enough, the transfer can potentially succeed. And by relatedness, we mean they could be through the same language family like Thai and Lao, or use the same script like Hindi and Marathi. Javanese and Indonesian are also closely related, and thus the example of zero-shot transfer that we're looking at here is likely to succeed. Once the low resource entity is encoded into a vector representation, we can simply compute its cosine similarity to the encodings of all the entities in the English knowledge base and select the top scoring entities as candidates. So the second thing that we propose here, apart from the zero-shot transfer, is that we realize that scoring the entities with respect to English may not always be ideal, as the low resource entities are likely more similar to those in a closely related high resource language than to English. So to take advantage of this, we introduced candidate retrieval through pivoting with the data in the high resource language. So instead of scoring English entities to find the best knowledge base link, we instead calculate a similarity score with the entities in the closely related high resource language that we train the model on. So to score a specific English knowledge base entry, we calculate the cosine similarity of the encoding of the same knowledge base entry, but translated to a closely related high resource language. And the intuition is that if the languages are closely related, it's easier to link to the high resource language than directly to English. And obtaining such parallel entities is straightforward because high resource languages typically do have bilingual lexicons to English. So we use the high resource language as an intermediate between the low resource language and English. So for example, we would link a Javanese input named entity to an Indonesian entity instead of directly linking it to the English knowledge base. So how does this look with our model? If we want to get the score of an English knowledge base entry in the United States, we would encode its parallel entity in Indonesian using the LSTM trained on the high resource language. We would encode the low resource input named entity mentioned with the same LSTM as we did before with zero-shot transfer, and compute the cosine similarity between those two encodings. So our overall method, which we call pivot-based entity linking, attempts to find the highest scoring knowledge base entries by calculating the similarity of each English knowledge base entry itself with the input named entity, as well as the similarity with the parallel high resource entity. So it involves zero-shot transfer for encoding the low resource language entity mentioned and pivoting with a high resource language. We also calculate similarity with the English entity because in some cases, the low resource language entity may be closer to English, or in other cases, the corresponding high resource language entity doesn't exist in the bilingual lexicon or on Wikipedia, so we won't be able to compute the pivoting similarity. And the final score for a particular English knowledge base entry is the maximum of these two similarity scores, either directly to English or pivoting through the high resource language. Finally, we also notice that although the languages may be closely related, they could use different alphabets or writing systems. And in this case, the character level LSTMs, if we train them on a high resource language, they won't transfer to a low resource language that has a different script. Instead, we propose converting all of the data to the phonological space using the International Phonetic Alphabet. This is an alphabet which is language universal and essentially represents how the words are pronounced. For example, Lao and Thai are closely related languages, but use different scripts. And in this case, the zero-shot transfer isn't going to work. However, if we train and test the model in the IPA space, we see that the entities are actually pretty similarly represented, and the zero-shot transfer can potentially succeed. So for our first set of experiments with the proposed pivoting model, we train models on 53 high resource languages that can potentially be used for transfer. We test on 9 low resource languages listed here. So as you can see, all of the languages use different scripts and come from different language families around the world. So the first test set that we use contains parallel article titles from Wikipedia. So it's basically the names of the articles from Wikipedia, and we're trying to link them from the low resource language to English. So we train all our models only on the high resource languages, and we use the data from the low resource language only as test data. So for the first couple of experiments that I'll discuss here, we only look at the top scoring candidate and check whether that is the correct entity link or not. And later in the talk, I'll show how the accuracy of the model improves if we look at a larger list of top scoring candidates. So the first baseline is the translation-based baseline, which previous work has used, where they use existing bilingual lexicons to translate the input entity to English. And you can see the entity linking accuracy in the graph. We also compare with the encoder model described earlier. So this just uses zero-shot transfer using only similarity to English, and it doesn't do pivoting through the high resource language. This actually improves the accuracy quite a bit. But once we add pivoting with a manually selected pivot language based on our prior knowledge of language families and other linguistic properties, we see that this model performs much better than the translation baseline and the zero-shot encoder baseline. Finally, we see that when we use multiple pivots, where we attempt to transfer from all 53 potential pivot languages, this gives us a small improvement in accuracy over manually selecting the pivot language. So next, we also conduct experiments on full documents from news sources, blogs, and Twitter for 2 low-resourced Ethiopian languages, Tigrinya and Oromo. So the graph here shows the entity linking accuracy. We compared the translation baseline and the encoder baseline to our manually selected pivoting, our pivoting method, where we manually select a high resource language to transfer from. So we see that even though the translation method is supervised, it doesn't work very well because the lexicons for these languages from Wikipedia are very small. We see that pivoting does work much better for Tigrinya than Oromo. And this is indicative of the fact that a closely related pivoting language is necessary for our method to succeed. So we use Amharic as the pivoting language for Tigrinya, and there and they're more closely related than Somali, which is what we use as a pivoting language for Oromo. We also analyze the utility of the proposed phonological transfer method. So this graph shows the average accuracy of pivot and of high resource and low resource language pairs when we transfer in the original script versus IPA. And then and next to that, we can see the same numbers for when the scripts are different. So when we transfer in the orthographic space, or when it's in the same script, so when we transfer in the original script, it actually works a little better than IPA. But of course, as expected, the orthographic transfer completely fails when the scripts are different. And when we use the phonological representations, this leads to much better zero-shot transfer. We also look at how adding a small number of low resource samples to the training data can affect the accuracy of the entity linking system, because more often than not, we do have a few examples that we can use to improve the system in the source language itself. So the graph shows how the accuracy changes with an increasing number of low resource language samples that are added to the high resource language training data that we use for the entity linking model. And we see that for languages that are very similar, like Javanese and Indonesian and Hindi and Marathi, there's only a small improvement as we add more samples in the source language itself. We see that for the languages where we do phonological transfer, like between Telugu and Tamil and Bengali and Hindi, the improvement is much more pronounced in terms of entity linking accuracy. Finally, we look at how using our method as candidate retrieval can potentially help a downstream disambiguation system. So this is the accuracy for each of the languages. So this is when we just look at the top one candidate. And as you can see, it's quite low for some of the language pairs. So when we look at the top 5 candidates, the recall increases quite a bit. It doesn't increase too much for languages that already have a pretty high accuracy at the top, but the top 5 list typically contains the correct entity for languages that don't start off with a very high accuracy. And a similar trend follows as we go up to the top 100 candidates from our method. And this is pretty typical because the knowledge base contains millions of entities. So for the downstream disambiguation system, looking at maybe 30 or 50 candidates is pretty standard. So just to conclude, we present pivot-based entity linking, which is a method that leverages high resource languages for zero-shot transfer. We see an average improvement of 17% over baseline systems. We also propose phonological transfer, which allows pivoting between languages that don't use the same script, and this improves the accuracy on average by 36%. And although we do have some follow-up work on this where we actually improve the pivoting-based method that was done more recently, other future work could be for using a single universal encoder for all the languages, predicting the best pivot language for a specific named entity. So right now we either manually choose the pivot language for the whole language, not per input entity. Or we just use all of the languages together, but it might be interesting to see whether we can actually predict the best language for a specific entity. We'd also maybe like to try combining the orthographic and phonological models to perhaps improve the accuracy. So yes, that's all I had. And there are more details about the model and more experiments and language-specific analysis in the paper if you're interested in learning more. This paper was published in AAAI last year, and the QR code has the links. So, so yeah, I just want to say thank you all for attending the presentation, and a special thank you to the organizers of the colloquium for giving me the opportunity to to present some of my work that was supervised by Jaime. And yeah, thank you so much. And I was really fortunate to have Jaime as my advisor, and I'm so glad I could share some of the work we did together with everybody. Thank you.
Okay, thank you, Shruti.
Hi everyone, I'm Zirui. Today I'm going to present our work at ICLEA this year. It's called Cross-lingual alignment versus joint training, comparative study and simple unified framework. This is a joint work with JT. He's also on Shruti's paper, so he should be really presenting today instead of me. And of course by Jaime. Yeah, a little bit about myself. I'm a fourth or eighth year PhD. I've been here for a long time, since I finished my undergrad here as well. I work on transfer learning, multilingual models, and I'm very fortunate to be advised by Professor Jaime G. Carbonell in the past. And I'm still considering myself as one of his students. So for this paper, we actually making two major contributions. The first one is to conduct a systematic study of two popular cross-lingual word representation. And the second one is that we propose a unified framework to combine those two. Yeah, to start with, just a little bit background. Word embedding or word representation is obviously a fundamental building block for modern NLP for many tasks. And so when we considering trying to build a cross-lingual word embedding or representations, what we really need to solve is how to align words with similar meanings together in a vector space that they are close to each other, and also considering their relative similarity. So in this left graph, for example, we can see words. There's a Chinese word called 下跌, and the English word is fall. Those two words means the same thing. So ideally, we want them to stay together. To train these, so once we have such aligned representations for two or more languages, we can utilize these as inputs or as initializations for any downstream task. That includes like name entity recognition or translation, or et cetera, et cetera. So to build, in the first place, finding such cross-lingual representations, there are two paradigms. One is alignment, and the other one is called joint training. The alignment method is more like the traditional way of how to train a aligned cross-lingual representation. The idea is simple, that we already know how to train monolingual embeddings. So we first train them independently using any method, for example, English and Spanish. And then in the second step, we need to obtain some dictionary between these two languages. This dictionary could be either given, like a real dictionary, or it could be synthetic, like just just assuming similar words that have similar spellings or have similar meanings, etc. And based on this dictionary, we can then learn a projection matrix W that project one vector space to the other so that they are aligned. Here on the right, here is an example, like minimize the distance between the projected space and the target space. and these two spaces should be aligned according to dictionary D. So that is like the more traditional way of doing this. This could be applied to both contextualized and non-contextualized word embeddings. And more recently, I guess more popular is the joint training method, where what it really does is just the first steps of alignment method, which is basically just train a word representation by just treating a large corpus that is concatenated by 1, 2, or many languages and just train it. There's some famous example would be multilingual BERT or cross-lingual language models. Even recently, like GPT-3, they are trained on many languages actually. So this could all be considered as a joint training approach. So the questions that we ask is basically, what are their pros and cons, and which one is better than the other? So this is an example of joint training, where the green parts are or considered as shared between the two languages, English and Spanish. And we can see some language-specific tokens like red and blue. So we can see that the majority of words are actually shared, which should not be the case because apparently, although these are two similar languages, many of them are still not shared. Like you wouldn't consider English word the to be a word in Spanish. So that is what we call oversharing. And the second thing is that we can find that the words are not aligned well. We can see two long tails on the right and left. Yet some prior work actually have shown good results using these embeddings, and we want to know why. So on the other hand, there are also some problem with alignment. Alignment, as we said, they are trained independently. That means their vocabulary are independent. So they have literally zero sharing. So we call that undersharing. And they have some not very realistic assumptions of the monolingual spaces. So that could also be problematic. So given these pros and cons, we design a unified method. We call that joint align. What it really does is that we first obtain a joint trained cross-lingual word representations that we call joint initialization. And then we reallocate a vocabulary. That means that, for example, English are reds. In the initial case, there are only a few words that are considered to be English. We recalculate their appearance ratio in each corpus and then assign the shared word back into English and Spanish, so that now you can see we have much more English and Spanish specific words. And then finally, we do another step of alignment refinement, which basically align this large red part to the large blue part, so that you can see now they are aligned well. So basically, the reason why we want to do all of these is just to alleviate the both shortcomings of either methods, such that we want to obtain something that is well aligned, like in the right figure, and also that has right amount of sharing, not too much, not too less. So yeah. So to evaluate all these, not only our method, but also like the joint training and alignment, we actually did it on 3 different types of tasks. Bilingual lexicon induction is really just word translations, but they are considered to be de facto tools to evaluate cross-lingual word representations. Basically, given the words, what's the translation of the words? And cross-lingual name entity recognition, and also we also consider unsupervised machine translation. So first on the bilingual lexicon induction, we have a plot here that shows the three methods. Actually, they're not three, but we just concatenate everything. We call it best joint, which is the best baselines we have, or best align, the best alignment baseline we have. So compared to, first we can compare joint and alignment, as we can see that alignment much outperforms joint in this case, which is consistent with our prior assumptions or findings that joint does not align embeddings well, but they have a better sharing. Of course, our methods outperforms both and achieve state of the art at the time. I'm not sure if they still are, to be honest. I think they are. Another thing is that we find that there are a lot of words that are actually shared in the testing set of the word translation task. That is like mainly aligns in the circle on the right, the purple circle on the right, or the pink circle. What it means that, for example, in the test set of English and French, there might be a specific token, let's say Donald Trump, and that is considered to be a translation of itself. Should it be considered a translation of itself? Maybe it should, but it actually gives an extra benefit for joint training because they are automatically shared, and it is considered to be the translation of itself anyway. So we just remove those and just consider and then compute the accuracy again on the rest, and find out that the joint training now actually have almost zero accuracy. What it really shows is the two long tails here, that they're actually not well aligned at all. So this highlights the oversharing problem. But then we might ask, if they are not well aligned, then how could people possibly consider using it? That sounds useless. They are actually useful. As I said, prior work, in fact, also now work, joint-trained word embeddings are actually improves the machine translation task. Here we, for example, on the left, we can see comparing, it not only outperforms alignment, it also actually outperforms supervised joint training. Now notice that supervised joint training is technically different from unsupervised joint training, in that supervised joint training actually also has no sharing in the, at least the one that we use, has no sharing in vocabulary. They are trained independently. So what this really shows is that sharing is important in this case. As we can see on the right, if we compare the blue line with the green line, we can see that at the very beginning, the first few epochs, the alignment method is better than unsupervised joint, which makes sense because we know that they are initially better aligned. But then we can see that unsupervised joint gradually outperforms alignment, which could be possibly explained by the fact that by further training the model, having some sharing actually serves as an anchor that could further improve the performance. So for these reasons, actually, unsupervised joint has many benefits, not because of that it could achieve some good results, but also because nowadays unsupervised data are much more easy to get, and training these models are much easy conceptually. Like you don't have to do alignment, and it's computationally cheap to train a large model on many TPUs. Yeah. So that highlights the benefits of using joint training. And one last point from this slide, of course, is that our joint align method actually outperforms the rest, which is a good sign. So it actually, because it performs better at the very beginning, because we aligned it using the alignment refinement, and it also consistently outperforms in the later epochs because it actually is also shared properly. So that highlights the importance of both effects. And then lastly, we also evaluate on the cross-lingual NER task, which basically you train on English and then test on, and then do zero-shot transfer to one of these languages. What the takeaway from here is really just that our method is applicable to contextualized embeddings. Right at the time when we did this, it was like a year ago, or almost a year ago, which there are still not too much, which XLM Roberta hasn't been released yet. So we actually just focused on the MBERT, multilingual BERT at that time. We showed that our methods, we can further align multilingual BERT to achieve better results, which is confirmed by further studies that's after our publication. So that's a good thing to know. So finally, just some final thoughts on cross-lingual NLP, which is really what's been highlighted in our work, is the comparison between sharing and undersharing and oversharing. So nowadays, many models actually try to maximal share things like embeds. All parameters are shared between languages. So in actually one of our recent work to be appeared at EMLP soon, we actually find that this is not the case, where we can see on the figure here that on the left shows the parameters that are important to to English, but not to Arabic. On the right, actually parameters that are important to both of them. So what it really shows is that there are some parameters that are language specific, like they are not that language universal. So just a possible explanation that having bad sharing can lead to some undesired effect. On the other hand, it's just possible that finding some better sharing either in the vocabulary or in the parameter itself could be improve the general performance of cross-lingual models. So yeah, that's basically sums up everything in this single paper. We basically compared two popular methods and show that they are not dominant, like none of them are dominant, neither of them not dominant. Their performance are task specific. And we further highlight that optimal sharing is important. Either way could hurt the performance. Our methods also is the first one to combine these two lines of research. Paper and codes are available, so feel free to read, cite, use, whatever. And yeah, final thank you to Jaime, who has been advised me for 3 years. Yeah, that's it.
Okay, thank you.